We used to think atoms had electrons orbiting the nucleus, like planets orbit the sun. Now we know better. Instead, imagine taking many snapshots of an atom. You would find the electron at one location, then at another, and then at yet another. After a very large number of snapshots, you would see the probability of finding an electron at any point in an atom. This collection of locations is called an orbital. An orbital is often depicted by drawing a surface inside of which the electron is found 90% of the time. This particular surface, a sphere, encompasses the lowest energy orbital, the 1s orbital of an atom. Another way to visualize this orbital is to cut a slice through the sphere. In this representation, brighter colors indicate a higher probability of finding an electron at a certain location. Because the 1s orbital is spherical, these values depend only on the distance from the nucleus, not the direction. Either one or two electrons can occupy one orbital. The two elements with electrons only in the 1s orbital are hydrogen and helium. Lithium and beryllium atoms have electrons in the next highest energy orbital. The 2s orbital is spherical, like the 1s orbital. It's larger than the 1s orbital and has a nodal sphere where the electron is never observed. Although the probability of finding an electron is greater than or equal to 0 at all locations, the function that describes an orbital, the wave function, has both positive and negative regions. As a reminder of this fact, the green areas indicate positive regions of the wave function, while red areas indicate negative regions of the wave function. The next 6 elements have electrons in the 2p orbitals. Each 2p orbital points in a specific direction, unlike the spherical s orbitals. The surface encompassing the 2py orbital points primarily along the y-axis. A nodal plane, in which the electron is never observed, is located in the xz plane. The 2px orbital is identical to the 2py orbital, except that it points primarily along the x-axis. The nodal plane is the yz plane. The third p orbital, the 2pz orbital, has its lobes directed along the z-axis. The nodal plane is the xy plane. These 2p orbitals form a set of 3 that are equal in energy and can be occupied by up to 6 electrons. Sodium and magnesium, the next 2 elements, have their chemically significant valence electrons in the 3s orbital. Like other s orbitals, the 3s orbital is spherical in shape. It is bigger than the 1s and the 2s orbitals and has 2 nodal spheres. The probability of finding an electron in this orbital depends only on the distance from the nucleus, not the direction. The next 6 elements have valence electrons in the 3p orbitals. Like the 2p orbitals, there are 3 3p orbitals. Each of these orbitals points primarily towards the x, y, or z axes. Each 3p orbital has 1 nodal sphere, and every 3p orbital has 1 nodal plane. These orbitals form a set that can be occupied by up to 6 electrons. Potassium and calcium have valence electrons in the 4s orbital. The 4s orbital is larger than the 3s orbital, but is otherwise similar in shape. The 4s orbital has 3 nodal spheres. The next 10 elements, the transition metals, have valence electrons in the 3d orbitals. 3 of the 5 d orbitals look similar to each other. Each orbital has 2 nodal planes, and the lobes of these orbitals bisect the axes. The 4th orbital is formed by rotating the dxy orbital until its lobes point along the x and y axes. This orbital is named the dx squared minus y squared orbital. The 5th d orbital has a unique shape. Its 2 nodal surfaces are nodal cones. This orbital is called the 3dz squared orbital. These are the orbitals of the valence electrons of the 10 transition metals. The next 6 elements have valence electrons in the 4p orbitals. Like the 2p and 3p orbitals, each 4p orbital primarily points toward an axis. Each 4p orbital has 2 nodal spheres. It also has 1 nodal plane, which defines the position of its lobes. The 10 second-row transition metals have valence electrons in the 4d orbitals. These orbitals resemble the 3d set, with each orbital having 2 nodal planes. In addition, each 4d orbital has 1 nodal sphere. A 45-degree rotation of the 4dxy orbital produces the 4dx squared minus y squared orbital. The 4dz squared orbital has a nodal sphere, in addition to the 2 nodal cones that define its shape. The 14 elements in the lanthanide series have valence electrons in the 4f orbitals. There are 7 4f orbitals. Each 4f orbital has 3 nodal surfaces. The z squared y orbital is transformed into the z squared x orbital by a 90-degree rotation. The x cubed f orbital is related to the y cubed f orbital by a similar 90-degree rotation. The fxyz orbital looks like a d orbital with an extra nodal plane. A 45-degree rotation of this orbital forms the 6th f orbital, the fx squared minus y squared z orbital. The 7th f orbital, z cubed, resembles the dz squared orbital with an additional nodal plane. This is the orbital basis for the periodic table. Other orbitals can be generated just like those shown in this video. Atomic orbitals help us to understand the arrangement of all the elements and many various chemical properties in a logical fashion.